Okay, so what we will be doing today is TWRR question. We will look at one example, very simple. We look at that. And then in your portfolio mathematics, we will spend some time particularly understanding portfolio applications with normal distribution, the equations about portfolio return and standard deviation. We also see that in portfolio management, so I'm not going to double review that. So we will keep that for portfolio management. We'll just see the quantitative aspect of the portfolio math topic, and then maybe a bit of sampling and hypothesis. Time-weighted rate of return. This is one of the other ways in which you can measure returns for a fund or a portfolio that you're looking to analyze. And this is, in fact, one of the requirements in your GIPS, right? So that you show, apart from your, you can show money-weighted return, but in terms of the presentation, time-weighted return is a kind of a mandatory one. So what we will see for computing TWR is you first calculate the holding period return before any major cash flows, right? So prior to that, very simple, you just have to do a HPR. Then if it is within a year, so if the HPRs add up and they are less than a year, you just have to join them. So your TWRR will be the 1 plus the R1 multiplied by 1 plus R2. So you're just compounding that. If the TWRR is for multi-year, more than 1 year, so this is less than or equal to 1 year. If we want to compute TWR for greater than a year, so then this computation will be a geometric return formula. So let's solve one problem on TWRR. I want to give just two periods here. So let's say I have on Jan 1st, my account is starting with 100,000. And then on April 1st, I had a cash inflow of plus 20,000. And my account balance, ending balance here is 130,000. Then on December 31st, let's say the account ended at, so this ending balance of 130,000, let's say this is after the cash flow. And then on December 31st, let's say we had the beginning value, the ending value is going to be the starting value, 130,000. And then we end on December 31st as 155,000. Okay, something like that. Very simple. I just want to illustrate this computation. I don't want to make it too complicated. So just 2 periods, Jan. So we have a cash flow happening only once in this example. I have an inflow of 20,000. That's the only cash flow. So we are going to separate this entire 1 year into the first 3 months, Jan 1st to April 1st, and April 1st to end of the year. And we're going to compute your holding period return. So your initial value for the first period, so starting with 100,000, my period 1, my P1 is 100. So the ending balance is 130. The cash flow was 20,000, which means prior to the cash flow, you need to see what was the asset appreciation. So my ending balance would be 130 minus that cash flow. I have to remove the effect of the cash flow. This is including that cash flow of 20,000. So my P1 would be 110,000. And my starting value, what they said, was 100,000, which means my HPR1 is 10%. For HPR2, period 2, my beginning value is 130 and my ending value is 155. My HPR is going to be 19.23%. Now, if we just have to link them for the TWRR, very straightforward linking, 1.1 multiplied by 1.1923 minus 1. So our TWRR is 31.1%. So I did this for less than a year. Now we will have to probably do one illustration that you can try when it is more than a year. Okay, so let's do that one. U1 is asking, why are we removing the 20,000? See, we are looking to calculate the holding period return. This 20,000 was not invested at the start of the Jan 1st. It was invested on April 1st. So when I'm looking at the return, that 20,000 is not a capital appreciation or a return. So I can't include that in my holding period return. I said there was a cash inflow of plus 20,000 on April 1st. And after that cash flow, the ending balance is 130,000. Including that cash flow, I said is 130,000. So the return was only 10%, not 30%, because 20,000 was just a investor cash flow that we can't include in our holding period return calculation. And again, for the second period, you will have to include the starting value with that 20,000 of cash flow. So 130 here, we should not subtract that 20,000 because the starting value is, in fact, the asset value is 130,000. And then from there, we are moving to 155,000. So holding period return will be 25,000 on the initial starting value on April 1st of 130, which is 19.23. Then you just link it and your total time weighted return is 31%. Make sense? Now let's do a multi-year. So 3 years, let's keep it easy. So let's start with the beginning value at year 1 of maybe again 100,000. I'm going to write it in K. All of these are thousands, so 100K. And then the cash addition. So this one, let's say, is 10,000. And the ending value is 121,000. Is 121,000. Now here again, the cash, initially we are investing 100. This cash is assumed to come in at the end of the period. You will not use that for your return calculation. Now, there might be some cash that the instrument itself gives, like say dividend. If that is given, that needs to be included in the return calculation. If there is a dividend, so let's say there is $1,000 dividend, and then the ending value is 121. If dividend or interest is obtained, that will be part of your holding period return. But the cash that the investors are investing, you can't use that if that is because that's not a return in that period. That's something that the investors are giving in additional funds in that period. Now the year 2, so we will be starting with 121,000, and then the cash, we will have one more line item which will say cash at the beginning. So here let's add cash at the beginning itself, 10,000, and let's say the dividend was 5,000, and the ending value here is 148,000. Okay, and then the next year 148, cash 0, dividend 5,000 again, and we ended at 160,000. Okay, let's compute the TWRR. So let's do the holding period return for first year, second year, and third year. Once you have your holding period return, please calculate the geometric return, and that will give you the annualized time weighted rate of return. You can send in your HPR one by one, year 1, 2, 3. You can send in your values as soon as you get it. And then finally, to compute once you have those 3 HPR, your annualized time weighted rate of return is going to be 1 plus HPR1 multiplied by 1 plus HPR2. So this is 3 periods. So raised to the power 1 by 3 minus 1. That's your geometric return that we are doing there. So year 1, the return is 11,000, right? So my ending value is 121, but I should not include this cash that we received at the end, because that's not a return, right? Any of this cash is not a return. It just adds to the value, right? Whether you have to include it in the P0 or P1 is the question. If it is a beginning cash, then your P0 gets starts with that. If it is an ending cash, the cash comes at the end of the period, end of the year, then that is going to be only at the ending value, but you should not use that in your return computation. Your return is going to be 121, but I need to subtract that 10,000. That is not actually a return. So 111,000 minus 100,000. And then you are also getting a dividend of 1,000. If they say it is reinvested, then it will be part of the value. If they don't say anything, that means you're taking that dividend out. The dividend is paid out. So you will add that there. So 111 minus 100 plus 1 divided by your starting value of 100,000, your holding period return is 12%. Your second year holding period return computation, you're starting with 121 plus that cash goes into the first time frame itself. So I'm going to have subtracting 131 because that's the P0 there. My P1 is 148. And then we also received a 5,000 of dividends. Starting value is 131. What is your holding period return here? And that is 16.79. The last one is a simple computation. So you have 12,000 in capital gains plus 5,000 in dividends divided by your initial starting point of 148,000. So this is 11.48. Let's do this one. 1.12 multiplied by 1.1679 multiplied by 1.1148. All right, so now take third root, y power x 3, 1 by x, minus 1. So my annualized TWRR is 13.39. So you have to be careful. If it is just a regular within a year time weighted rate of return, you just link it. You don't have to do the geometric return. We are just linking in the first one, the 31.1%, it is just linkage. So 1.1 multiplied by 1.1923 minus 1, and that gives you that 31.1%. Okay, so now moving on to portfolio mathematics, I really want to focus on the part that is kind of new in your learning module 5, because a lot of this overlaps with portfolio management, and we are going to be spending time there. At the time we will look at those portfolio computation of expected return and standard deviation. Now, one thing that we have not spent a lot of time is to talk about the random variables and the distribution. The distribution that we should know is the normal distribution or the bell-shaped distribution, which we often use in most of our assumptions of the returns. Particularly, the returns are assumed often to be normal distribution, though in reality there are some deviations from normal distribution. The good thing about normal distribution is that we can easily predict what is the chance of us being above a certain return or below a certain return. If I assume if I assume that the returns are going to be normally distributed, it's a lot easier. So oftentimes you will start there, then maybe make some tweaks. So in a normal distribution, the good thing is you are having a symmetrical distribution. That is, your mean is equal to your median, is equal to your mode. So it is symmetrical, that is, the skewness is 0, and we have a kurtosis. Kurtosis measures the peakiness or how long the tail is. So the kurtosis value is 3. So this is for any symmetrical distribution, but obviously that's true for normal distribution as well. And your skewness is 0. If the kurtosis is 3, anything above 3 has a higher peak, right? So this part we know, if I have something like that, like a taller one, and so you have more longer tail and a higher peak, but you don't have as much in the center, right? There's not much distribution happening in the center. So something like that, that is having a kurtosis more than 3. Okay, so 3 plus. What is the name of this kurtosis? What do we call the distribution with the kurtosis more than 3? A distribution more than 3 is called as leptokurtic. So kurtosis more than 3. And anything less than 3 is called as a platykurtic. And this one, the kurtosis equal to 3, is sometimes referred to as a mesokurtic. Now, if people find this a little bit strange, this 3, you can subtract the 3 from the kurtosis computation. See, the kurtosis and skewness computation is unlikely. They will ask you this slightly, we don't have a calculator function. It's a slightly lengthy calculation. And so in my review, I'm not going to focus on that. That's not a high priority one. So what you need to understand is this concept of what is kurtosis. The kurtosis tells us how much of the values are available in the extremes, right? So if I have a leptokurtic, the distribution is going to, I can't draw it here, but something like this, right? So I'm going to have a longer tail or fatter tails. That's the characteristic of a leptokurtic. And to make it a little bit easier, maybe you can subtract 3 from the kurtosis combination, and then you can get what is called as excess kurtosis. Excess kurtosis is your kurtosis value minus 3. So in this case, the symmetrical distribution will have, the mesokurtic will have a 0, your leptokurtic will have positive, and your platykurtic will have negative values for kurtosis. Skewness, on the other hand, is talking about the symmetrical nature, right? If you have more values on the, so the skewness can be either on the left side or on the right tail. So if I have a distribution, so in this one, which is the left skew or the negative skew, which is the common scenario we see in the markets, it's often a left skew distribution. So if you look at what's the returns for Nifty or S&P 500, it tends to be a left skew. That is, it has the left tail is longer or fatter than the right tail. So you have a distribution something like that. I don't think I drew it super well, but you get the idea, hopefully. The idea is that the left side has a longer tail, right? So this is a fatter left tail. And in this one, your skewness is going to be negative. We said for the normal distribution, skewness is 0, symmetrical 1, where mean is equal to median is equal to mode. But in the case of left skew, what has happened is that it has shifted. So you have more values. See, when you think about market, most of the time we are going to have positive values. If this is the center 0, and most of the time we are going to have some small positive returns. But when you have the outlier on the negative side, there are more of them. There are often outliers of the left of the distribution. So the data is stretched. So you have a lot more than what the normal distribution will predict as the down days, right? But you have more often, most of the values tends to be on the skew, mostly on the positive side. So here, my mean value, right? My mean value, this is my mode, and your median is the center one. So because it's a left skewed, what's going to happen is it's going to be your somewhere your median might be somewhere here. And then because of this extremely large negative values, your mean might be even to the negative. So what's going to happen is your mean is going to be lower than your median, and your median is going to be lower than your mode. So this is your left skew, and everything reverses in the right skew or positively skewed. The positively skewed, you have something like this, right? So here you have the mode. So the mode on the positively skewed is going to be on the left side. So you have more values, fatter right tail. So this is your positively skewed or right skewed. So your skewness is going to be greater than 0. It's positive. So your mode is there, and then you have your median. Median is going to be somewhere in the middle, and then you will have your mean. more to the right. So your mean is going to be greater than your median, and your median is going to be greater than your mode. That's our right skew. Okay. Now, the whole point of all of this is just to understand the distribution characteristics. We already saw two characteristics in the morning. One is your mean and standard deviation. For a normal distribution, we don't care about kurtosis and skewness because this is symmetrical and that is perfectly, in terms of peakiness, it is mesokurtic, it's symmetrical, and excess kurtosis is 0. So we usually don't need this. We only need mean and standard deviation to describe a normal distribution. So when I have a normal distribution, we have some special characteristics. We have talked about this in the class many times, and you guys all probably know. So if I have this mean here, and I have one sigma to the positive and one sigma to the negative, and we know that this area is roughly 68%. It's not like proper, but you want to get the idea, right? So you know how to get these values also. So this shaded area is 68%. Now, how do we do this? We use the standard normal table to get the areas. A standard normal table, or Z table or Z table, is a special type of normal distribution called as the standard normal distribution. So these are the values for a standard normal distribution. See, a regular normal distribution can have any mean. So if I look at Nifty and say the average return is 14% and standard deviation is 20%, so something like that, right? So this is what you will be seeing, something if for a Nifty or some kind of an Indian equity market. But we can't use this normal distribution and find the values directly. So we need to do a transformation or standardization of the normal distribution. The standard normal transformation is very simple. All you have to do is use this formula x minus mu divided by standard deviation, and that will give you the equivalent value in the standard normal table. So this is also called as your Z value. Okay, so we just transform a regular normal distribution into the standard normal table. Okay, now how do we do this? So I'll give you one example. I'm sure all of you have done this at least a dozen times. So let me give you one example and convert this regular distribution into a standard normal distribution. So let's say my Nifty average return, population average return, mean return, just hypothetical, okay? And standard deviation of Nifty, let's keep it as 12%. Calculate probability that you will get returns above 18% in next year. So simple question. So you'll have to convert this Nifty values into a standard normal value, and then we will go into the Z table and find the probability. So before we get into the Z table, use the formula I just gave, the transformation, standard normal distribution transformation. Okay, so with the normalization formula, so you have your X value as 18, we said. That's the value that we are looking at to find. And my mean distribution, so the formula substituting x minus mu was given as 15 divided by standard deviation of 12, which is 3 by 12, 1/4, which is 0.25. That's my Z score. Okay? So basically we are trying to find, okay, what's the probability that the returns will be mu plus 0.25 sigma. So we are asking to find what is the probability of mu plus 0.25 sigma. And we can't use our regular mu and sigma, but instead we are going to use the Z table. We are assuming mean to be 0 and standard deviation to be 1. So we're going to go to our standard normal distribution table. So this is on the positive side. So this is on the right tail. The first thing you need to know is Table value represents the area to the left. Okay, for your Z table, it's the area to the left. It's not always like that. Some of the distributions you will see later on in hypothesis testing, the value they give is to the right. Okay, but for standard normal distribution, this table represents area to the left of the Z-score. Now we are looking at 0.25, we said. It's always a little bit tough to draw on this PDF. So I'm going to try and just get the values from here. So 0.2, and then I have to have the second decimal as 5. So keep coming down until we have 5 there. And it comes to 0.59871. What this represents is the area to the left. That's important to understand. So here, this 0.59871. So this is my mean of 0, and I have 0.25. Right? So we have converted our nifty returns and standard deviation in standard normal equivalents. And so what we have found is the area to the left of this standard deviation of 0.25 is 59.8%. But this is not what we want. What we want, if you look at the question, they said, what is the probability it will be greater than 18%? That is to the right side. The right side is the higher values. So we are looking at the unshaded portion, but the entire area is 100% or 1. So we can subtract 1 minus the left side area, 0.59871, and that should be like 0.4, something like 0.4, what's that? 0.59871. 0.40129. So the answer here, so the chance that we will get more than 80% from the standard normal table, looking at the right side of 0.25, we got that as 40.13%. Okay, so now hopefully everyone has a standard normal distribution table. If not, you can Google it. It's available in multiple websites. What I'm going to ask you to calculate is what is the chance, we will use the same Nifty, or maybe we'll change it. We'll change it to S&P 500. Let's say historical return is 14%, standard deviation of 11%. So we'll round it 10%. Calculate probability of return between 8% and 15% next year. Assume normal distribution. So if we assume this is to be a normal distribution for S&P 500 returns, what they're saying is the average return is 14%. We need to convert this to be 0%. That is, we are transforming this 14% to 0%. That's what standard normal transformation gets you. And my standard deviation is 10%, but we are going to assume that it is going to be 1. Right? So we are going to change that. So based on that, if you do the Z1, you get some value, and Z2, you will get some value. You should get Z1 as your 8%, 8 minus 14 divided by 10. So that will be 6 by 10. So it will be negative 0.6, right? And your Z2, as most of you had computed, it is 15 minus 14 by 10. Is positive 0.1. So what we are looking at is something like that there, something like that, and here. So this area is what we are looking to find. What is the chance the return will be within this area where my Z value is minus 0.6, and on the positive side it is 0.1. So use your standard normal table and calculate that. Question is online is how do we do minus 0.6? You will have a negative table, negative Z table. If you don't have, if you only have a positive table, that means you can find the area of 0.6, right? And you just subtract that. 1 minus n 0.6 is equal to n minus 0.6. Okay, because of the symmetricality, you can just subtract the value that you get for the positive Z score from 1, and it will be equivalent to the minus a z-score, the negative z-score. But you should, I mean, most of the time you should have both positive and negative values in the examination. So you can directly use the negative z table. In case they don't give it to you, it's not very difficult to get that value if you have. All right, so let's do this one quickly here. I'm going to look for 0.6 negative. So this is a positive table. So you can also find the positive value and subtract it from 1. But I have a negative value, so I'm going to just choose that. Minus 0.6, and it is 27.425. So this is 27.425. The area here, they are saying the equivalent area is 27.425%. So what is that area? That is this area, the white area, the area to the left. Always be careful about that. It's the area to the left. Okay, now let's find for 0.1. Let's find that for 0.1. It's positive 0.1 is 53.983. So this is this part. Everything to the left here, we'll use like a blue line. So the entire area. Right. So what we have to do, the blue line and the white line overlaps. We have to remove the white area from the blue area. So this part of the negative, we are not worried about. We are stopping at 8%, which is equivalent to a z value of minus 0.6. So all we have to do is to find this probability here of between 8% and we said 15%. We are going to find the normal value for 0.1. It's going to give all the returns below 15%, but I want to subtract the returns below 8%. So n that 0.6 negative. So we do that, and that comes to roughly 26.5%. So that's the probability of getting a return between 8 and 15. What is called as the Roy's safety first ratio. And to understand Roy's safety first ratio, we first need to know what is called as shortfall risk. Shortfall risk is the chance that the portfolio's return or value will fall below a certain minimum acceptable levels, right? So what is the chance? So if my portfolio return or the level, so my portfolio return is less than a specific return, right? So that is my shortfall risk. So Roy's safety first ratio, I'm going to abbreviate that as SFR, safety first ratio, is just your RP minus your RL, right? So divided by your standard deviation. You are going to calculate this SFR, safety first ratio, and then the next step might be to try to understand what is the chance, percentage probability that the return will be actually less than your minimum acceptable level, this shortfall risk. This R subscript L is the minimum acceptable level that we can accept or be okay with. What is the chance? So this one is given as the standard normal distribution n of the negative of the SFR. Okay, so just 3 steps. Okay, first of all, see what is your shortfall risk level. So you might have to calculate this RL using time value of money keys, and then compute your Roy's safety first ratio. Then just do n of the negative of the SFR. If you only have a positive table, then you will have to do 1 minus n of the SFR. Okay, so if they give you just a positive table, then you can do 1 minus n. So first thing is they might say, like, you know, they will give you a scenario. This person needs to save money for retirement, something, and you will calculate your I by Y, which is going to be the minimum return that you need, such criteria. In this case, we all know how to do TVM. So I want to give you this value. Let's say my minimum acceptable return is 5%. But you might have to compute this value based on the portfolio size or the return that this person is expecting. Okay, once we have this, we are going to calculate the safety first ratio. And for this, they will usually give a couple of portfolios and you will have to pick the one with the highest SFR. So they might say like the RP, 15%, 20, and something like that, 18, and the standard deviation. Okay, now let's do the SFR computation, RP minus RL divided by standard deviation. RP for the first one is 15 minus 5 divided by standard deviation of 10. So my SFR is 1. What about SFRB? So SFRB, a lot of you are saying something like 0.8. So it's going to be RP is 20 minus RL, so 15 divided by the 18. So that's some 0.833. And the last one, SFRC, I got the answer as 1.08 from UN. So I want to go with that. So this is what you're going to do. First, you're going to calculate your minimum acceptable level, but I gave you here, but in the examination, you might have to do this. So out of these 3 portfolios, which one do you choose? A, B, or C? The second step is to determine the portfolio. We want to go with the highest SFR, and that is C portfolio. Now, even with the C, there's a chance that we might go below the minimum acceptable level. The shortfall risk might happen. So to do that, you're going to do N of minus 1.08. So go into the standard normal table. If you have the negative, you can do that directly. Otherwise, you do 1 minus N of 1.08. So we don't have Excel, so we can't do like second, third decimal and all that. So I want to round this to N of 2 decimals. Minus 1.08 is your last but one column. So scroll down to minus 1.0. That is 14% roughly, I think. Okay. So there is a 14% shortfall risk, the chance that it will be below the shortfall level, right? So this is the probability that portfolio C's return will be less than 5%. So these are the 3 steps. Just very simple, just like how you did this computation of the probability using the Z value. So we are using the SFR like our Z value and using that to compute the probability of shortfall or the shortfall risk. Okay, so that's a wrap here. We will see you guys on Monday. Please continue with your ethics. It's almost a fifth of your examination is ethics. Make sure you continue prepping for it, solving questions from your learning ecosystem in CFA's LES portal. All right. Thanks, everyone. Thanks for joining today. Take care.